Director of TEQIP, to Head of the Department of CSC, Controller of Examinations, and Director of Innovation Technologies, and Director of Evaluation, Principal of JNTU University, Jagityal, Director of R&D and Cell, and Chairperson of the Board Studies for CSC and Allied branches. Beyond JNTUH, Professor um, Prasad sir has contributed as a member of Board of Studies, academic councils, and governing bodies of several institutions. He has also served as a visitor nominee of the President of to the Executive Council of MANUU, Hyderabad, and as a board member of the School of Computer and Information Science at the University of Hyderabad. In recognition of his contribution to academics, he has honored with the Telangana State Teacher Award in 2020. SAR research spans multiple cutting edge areas, including quantum computing, machine learning, data mining, and speech and image processing. He has published more than 150 research papers in reputed journals and conferences, and he has successfully guided 34 PhD scholars and 3 MS degree holders, spanning the next generation of researchers and academics. Um, Please join me with a warm welcome, Professor V. Kamakshi Prasad, sir. So over to
Yeah.
Kamakshi Prasad, sir. Thank you.
Good evening to all the participants. Thank you for a good introduction, a nice introduction. Uh, because of the uh, time factor, uh, I prepared some slides with these are all manually prepared with handwritten notes converted into PPT presentation. I think this is a effective way because we will be effectively connected with the document that I am going to share, because every piece of the document is easily understandable. I will add a few decorations, and I will share it with the organizers in the evening hours today, so that that will be added with a few additional stuff. But for presentation, I believe this 13 slides presentation will fulfill the objective. Uh, I will be now giving the presentation. All of you know, in fact, I'm repeating again. This I will share this presentation after adding few more things, a few more add-ons with the organizers. The organizers will in turn share this presentation with all the participants. So, as I mentioned in my previous class, and probably one or two resource persons must have touched the Grover's algorithm. What is its impact, how it is so distinct and unique. Because it is such a important algorithm. As I mentioned in my previous class, it has brought a big revolution in the quantum computing subject, physical quantum computer design. Grover, I'm repeating because once again I'm repeating what I told in my first class. Grover is a mathematician who proposed one algorithm, means a circuit, a hypothetical circuit, and conveyed a challenge to the architects to build a quantum computer. If at all they are able to come up with a quantum computer with a specified list of gates, this algorithm that what he proposed will be successfully executed for the purpose of searching. And in fact, this challenge has not gone waste. The architects have taken it in the right spirit, and they demonstrated a working model, and That's how Grover's algorithm was the first useful algorithm. Okay, and it has proven to be a sound alternative, best alternative to the traditional searching algorithms in using digital computers. So that is where the supremacy of quantum computers demonstrated for the first time. So that is the greatness of Grover's algorithm. So let us see the Grover's algorithm. As I mentioned, this is prepared by me. It is comprehensively prepared. I tried to touch all the aspects. Try to follow. If you certainly you will get some doubts, and please don't hesitate to ask me. So I'm starting it this way. So it is a function mapping from n bit pattern to 0 or 1 binary range, and it find x belongs to 0 1 this domain power n such that f of x is equal to 1. So it is typically a search problem. There are eight elements in the list. Only one is one. Remaining all are zeros. We are asking the system to locate the location, identify the location of one. So this is typically a search problem. Searching of an unsorted list. Okay, it is searching of an unsorted list. All of us know it is of complexity order of n. So it is f 0 0 0 is equal to 1, f 0 0 1 is equal to 0, like that f 0 1 1 is equal to 1, f 1 1 1 is equal to 0. So the system should understand, okay, where the location of 1. So it system should return 0 1 1 as the answer, address of the bit. So this is typically a problem of complexity theta of n. Okay, this is a classical computer. N is equal to 2 to the power of n because it's a bit string. But whereas in Grover's algorithm, it is guaranteed to find the solution in much lesser time, like root n, even somewhat lesser than the root n. So this is the promise of Grover. Let us see how it is realized. See, there are n varieties of cases. Okay, earlier I illustrated one case. Here it is another case wherein there are again domain is having 3-bit pattern address. So 0 to 7 is the address, and in the range we are having three ones. That means all the three are outputs. All the three are outputs. So this is because to make it somewhat mathematically illustrative, I took an example with three ones. That means three. If the system returns any one of these three, that is an answer. So all of you know direct notation. As per that, cat A means it is all searching. That means found. Okay, so it is same as this 1 1 1, and cat B is another quantum state which is having all the negations. Okay, 0 1 become wherever 1 is there, it is 0. Like that, this pattern is arranged. So out of so the summary is here cat A is equal to it's a superposition of 3 bits, extension of Hadamard gate. So what we are going to have 1 by root 3 of this, and there are 5 ones here. So 1 by root 5 of 0 1 1 0 1 1 0 1 is cat B. So if you see, this explanation is given here. Let A represents equal superposition of all inputs such that f of x is equal to 1. and let B is orthogonal to A. So wherever 0 is there in the B, that will be 1. Wherever 1 is there, that will be 0. So, this is bracket notation. So it is an inner product of two vectors that is equal to 0. That means these two quantum states are at a 90 degrees angle in between them. Okay. So this is a scenario wherein I defined cat A and cat B, and it is illustrated that they are at orthogonal locations to each other. Now let us see carefully. So let cat H is created using Hadamard. Let angle between cat B and cat H is theta. So we have seen earlier cat A, cat B. Now this is cat H.
Excuse me, sir.
Yes.
Sir, we are not able to see your slides, sir. Only first slide is visible for us.
Is it?
Yes, sir.
Oh, thank you. Thank you for alerting. I thought it is visible. No, there is some problem then. So, is it visible now?
Yes, sir.
Yes, sir. Visible, sir.
Oh, I was telling about this slide and now this slide. Okay, I will quickly repeat. Actually, it is not in the presentation mode. Is it in second slide? Now I move to third slide. Is it visible? Third, see
Yes,
at the
yes.
No, sir.
at the top right corner, I put the serial number of the slide. Three. Three
Yes,
is
sir.
visible.
Yes, sir, but it is not moving.
What about
Sir,
four?
Put
Four
it
is
in.
visible.
No, sir. Put it in presentation mode, sir. That
I'm in the
down,
presentation mode.
down.
No,
no,
which
sir. The first slide number is 0 actually. You
ah
are in correct third slide only. And yes.
see on top of the on right top corner, I put the serial number of the slide. Don't refer this slide bar or serial number. Here one. Okay, slide one is visible.
Yes,
Yes,
sir.
sir. Visible, sir.
Slide two.
Yes, sir.
Yes, sir.
Now I move to the presentation mode. This is slide 2. Now I'm moving to slide 3. Slide 3 is visible?
No, sir.
No, sir.
No.
No,
Okay.
sir.
Then instead of wasting time, what I will do, I will be displaying it in the this mode only. Okay. Is it okay?
Oh,
Yes, sir.
Okay, sir.
okay, sir. Okay, sir.
Good.
Now it's good, sir.
So we have seen this slide. And then I have explained this slide. So this is another illustration of 3 bits domain and 1 bit range, and one it denotes okay successful set successful. So there are 3 ones. So let A represent. So and we are going for direct notation. Cat A. Cat A represents equal superposition of all inputs, such that f of x is equal to 1. Okay, and cat B is just orthogonal to cat A. So wherever 1 is there, that is 0. Wherever 0 is there, that is 1. Are you following? So this is inner product of two quantum states, okay, cat A and cat B. No, it bracket bra A cat B. That is inner product. Inner product of these two vectors is 0. That is illustrated with a graphically like this. Okay, and then I move into the third slide. This is the third slide. Carefully listen. Here we will see the logic of Grover's algorithm. Let H is created using Hadamard gate. So let H is this is H, and let angle between cat B and cat H is theta. They are at an inclination of theta degrees. and then let initially x is equal to cat h. Now x is at the location of cat h. Are you following? So now our goal is to move this x to close to cat A, this location. How is this done? This is done by carrying out two reflections. First reflection is okay. See, this x is aligned with cat h. Okay, in the zeroth iteration. Now what happens? We reflect x over b. X. This is the b. When it is reflected, you will get this version. So this is a reflected version. After reflected with a theta, which is making originally theta degrees, is reflected. After the reflected vector will also make the same angle, but in the other side. Okay, this is the first step. And second step, reflect x. Now this new x is there. No, it is making an angle 2 theta degrees with h, cat h. Now I reflect this x over cat h. So this is 2 theta. So other side of the cat h, 2 theta will be the new location of x, new vector location x. So now originally it is aligned with the cat h. Now it is at a distance of, at an angular distance of 3 theta from cat b. Original here it is only 1 theta, but now this is 2 theta and this is 1 theta, total 3 theta. This process will be repeated. See, when this process is repeated a finite number of times, it is bound to come closer to cat A. Okay. Uh, is this clear? So now we have performed two reflections about first reflection about cat B and second reflection about cat H. Initially, X and cat H are aligned with each other, but once we perform these two operations, they are now separated. This slide is clear to everyone? Yeah, one of you please respond.
Yes, sir.
Yeah, this is a very simple. Okay. Next slide is also simple extension. All of you see, this part we have already seen. Okay, after first rotation, this was the scenario. See here, okay, only thing I added is theta plus 2 theta, 3 theta. Okay, that thing I added. So this left-hand side arrangement is output after first iteration. Now we see, now again, what we do, in the first cycle, we reflect about cat B. So then this is 3 theta. So at the downside, there is 3 theta. And then now I reflect this with cat H. The 3 theta plus theta is equal to 4 theta. So now with respect to this cat H line, when it is reflected about cat H, what I am going to get is 4 theta. This is the new vector. So 4 theta plus theta is equal to 5 theta. It is a 5 theta angle it makes with cat B. Are you following? So this is after second iteration. So after first iteration, see the summary. After first Grover's rotation, the x is located at a angular distance of 3 theta from cat B. After second rotation, it is at a distance of theta plus 4 theta, 5 theta, 5 theta. So now this can be generalized. How it is generalized? After kth rotation, it will be at a angular displacement of 1 plus 2k times theta. Okay. So this is every time it moves okay a little bit towards cat A. At one point of time, it will touch the cat A. So now, what is cat A? If you remember, cat A is the solution where the I am going there. You see here, cat A is the solution. So where 1 is present, that is our target. Are you following? So in this scenario, there are 3 ones, but the more likely case is only 1 remaining all are zeros, then 1 by root 1, and that 1 will be there, remaining all are zeros. Are you following? So if when there are more ones, so okay, the target will be reached fast. If there is only one, it may be reaching somewhat slow, but it is bound to reach. Okay, I think up to here everything is clear.
Yes, sir.
Okay. One of you please respond. Okay. And now I'm moving to the next slide, slide number 5. Now we see I have summarized the Grover's algorithm. Now what I have done? Create equal superposition of all possible inputs, that is cat h, and then it is a for loop. For timing, ignore this upper bound. Okay, upper bound is actually the complex time complexity. We will derive this. But now you see here, these two operations are well versed. First, we are carrying out reflection about cat B, and then we are carrying out reflection about cat H. And this process is repeated for a certain number of times. Okay. Once the upper goal is reached, okay, we measure X. Measuring X means we are having the address of the bit 1, okay, which is our target. Are you following? So so Grover's algorithm, when we put it on a paper, it will be very simple, and it is such a simple thing. Okay, so here cat A and cat B are defined. Already I explained how cat A and cat B are defined. So this is algorithm. So what is unknown here? This upper bound is unknown. We will see how this is computed. So now yet to do. What are the things yet to do? We have seen the algorithm, Grover's algorithm. So why we have pi by 4 root n rotations? See here pi by 4 root n. This is the floor. So floor of pi by 4 root n is the sufficient number of rotations to arrive at the solution. So the first question that we are going to answer is why we have pi by 4 root n rotations. And the second one is maths of Grover's rotations. And the third thing that we are going to see is quantum circuit for Grover's algorithm. And fourth one is working example. So these are the 4 topics which we are going to deal now. The first one, let us see. So this is actually our time complexity of the search algorithm. So we will see how this is actually arrived. All of you carefully see. I have taken different examples just for there is no any special reason. Okay, you can take any example. So I have dealt with 2 different examples, and yet it is third example is different. Now we see this function is known to you, and this is there are 2 locations which are of our target. So now A denotes what? A set A indicates where our required locations, list of required locations, 0, 1, 0, 1, 0, 0, where it is 1. So that is set A, and set B is other locations, other 6 locations, 0, 0, 0, 0, 0, 1, 0, 1, 1, okay, 1, 0, 1, 1, 1, 0, 1, 1, like that. So this is A and B. What is A? It is defined. Okay, X belongs to this domain, and where f of x is equal to 1. B is f of x is equal to 0. So corresponding values are given here. And all of us know cardinality of set A is equal to 2. Cardinality of set B is equal to 6. So let us denote it with small a and small b. Okay, now It is equal superposition case. What we are going to have is here you see cat A is equal to, there is a small correction, here. It is not comma, it is plus. Okay, and also here for cat B it is not root 2, it is root 6. 1 by root 2, okay, cat 0 1 0 plus cat 1 0 0, and cat B is equal to 1 by root 6. This one is root 6. So this is all pluses. Okay, I will revise and I will send it. Okay, now this is cat H. This is a Hadamard gate defined as, carefully see, 1 by root n sigma x is a member of n bit string, cat x, okay, is equal to root a by n cat a plus root b by n cat b. Okay, so you know what is A, what is cat A and cat B. So this is cat A. Please consider it as a plus symbol everywhere. So in our example, cat this H is equal to 1 by root 8, because there are totally 8 elements. This is cat x. Okay, x belongs to 0 1, a bit pattern of 3 members, and here it is 2 by a is equal to 2, n is equal to 8, 2 by n cat a. Yeah. Again, there is another mistake. Actually, this one is kept uppercase A. This is kept uppercase B. Followed. So this is. I hope it is. There are. I summarize the mistakes in this. Here, all the things are pluses. It is root of 6, and this is uppercase A, uppercase B. Okay, I will revise and send it to you all of. Yeah. So now we should understand how cat A, cat B, cat H, because in our graph these are the 3 initial entities. Okay, how cat H is defined like this. So this is a simple superposition, equal superposition. Cat of H illustrates a simple equal superposition of all the things. Okay, is it clear?
Yes, sir.
Yeah. Yeah. Now I'm moving to the next slide. Now we see. Now derivation for number of rotations. As I mentioned, number of rotations are in the for loop. I have illustrated number of rotations as pi by 4 root n. Okay, so now we are going to see its proof. So we know theta becomes what theta becomes after k Grover rotations is 1 plus 2k times theta. Okay, we have seen in the one of the earlier slides. And cat of h is equal to root over a by n cat a plus root over b by n cat b. Okay, this is also given in the previous slide. Okay, and then in polar coordinates, cat h is equal to sin theta times cat a plus cos theta times cat b. Okay, this is a simple trigonometric rule. So we can get the h location if theta is known to us. Okay, then sin theta times cat a plus cos theta times cat b. Followed. So when theta is equal to very small, sin theta is equal to theta. And let us bring an analogy Sin theta is equal to root A by N, cos theta is equal to root B by N. So sin theta is equal to root A by N is equal to theta. Sin theta is equal to theta. So this is what we are going to get. After k rotations, x becomes, so this is the initial h. After k rotations, this theta becomes 1 plus 2k times theta. So the same the see initially what happens, x and cat h are same, so this is a x location as well, but as the time progresses, x is a distinct separate entity. X is equal to sine of 1 plus 2k times theta cat a plus cos of 1 plus 2k times theta cat b. So now, what is our objective, our aim? Our aim is measuring of probability of measuring cat A. So probability of measuring cat A with one probability, 100% probability. That happens when, see, all of you know, in the quantum, any quantum qubit, okay, quantum state cannot be measured when we, okay, when we try to measure, it will be collapsed to one of the states. A qubit will be collapsed to one of the states. Are you following? So when there are n possible states, we compute the respective probabilities of each states and say probability for collapsing this quantum qubit to a particular state is nothing but, this is the formula. Okay, this magnitude square by this square plus this square, this magnitude square plus this magnitude square. So since it is a normalized vector, okay, this holds good. So then denominator is as per the trigonometric identity, it is sin theta, sin square theta plus cos square theta, it is equal to 1. Hence, what we are going to get is sin square of sin square 1 plus 2k theta is equal to 1. Is it clear? This is very important to understand this problem. You see, this is a quantum state. This is a quantum state. This is a qubit. This qubit can be collapsed to either this or this. For this to collapse to this one, okay, that means when probability is equal to 1, it will collapse to this. So, okay, the probability for measuring cat A to be 1 is nothing but, okay, this magnitude square by sum of these two magnitude squares equal to 1. And then eventually we are ending up at with sine square of 1 plus 2k into theta is equal to 1. So this is an important finding. Okay. Any doubts here? Is it clear?
Clear, sir. Clear, sir.
Yeah. This is important. Then rest of the things are easy. Sine square of 1 plus 2k times theta is equal to 1. Sine of 1 plus 2k times theta is equal to 1. Sine inverse 1 is equal to 1 plus 2k times theta is equal to pi by 2. And we substitute theta is equal to, see here. Sin theta is equal to root a by n. So theta is equal to root a by n. I am substituting, and by doing so, I will be getting 1 plus 2k times root a by n is equal to pi by 2. So 1 plus 2k is equal to, so this is a simplification, pi by 2 into root n by a. Are you following? So 2k is equal to pi by 2 times root n by a minus 1. Minus 1 is missing here. And finally, what I'm going to get is k is equal to pi by 4 times, pi by 4 times root 1 by n by a minus 1 by 2. So if a is equal to 1, what does it mean? What is a here? A stands for how many bits are the target bits. How many bits are the target bits? You see here. Target bits are 2. So a is equal to 2. If there is only one target bit, that is the most most time consuming activity. See, the logic is like this. When there are more than one targets, whenever first target is encountered, the system terminates. Suppose in the entire list there is only one target, okay, that will exhaustively, unless it reaches that particular state, it will not terminate. So relatively more tougher thing is a is equal to 1. So only one of the f of x value is equal to 1. Are you following? So now if a is equal to 1, there exists only one target value. Okay, then k is equal to pi by 4 root n minus of. Since it is minus of, okay, we have considered the floor value, not the rounded value. Are you following? So flooring, because it's like okay, we see in the line generation algorithm everywhere, wherever we subtract off from the real value, that is equal to the floor. Okay, not the ceiling or not the rounding value. Okay, so eventually I'm getting k because k is an integer. Okay, it cannot be a real value, number of iterations. So pi by 4 root n is the answer. So if you see here in this algorithm, the Grover's algorithm, the for loop iterates until pi by 4 root n times. Okay, now okay, that means it is much lesser than it is root n times pi by 4 root n times. Okay, this is what we computed in this slide. Okay, is it clear?
Yes, sir.
Yeah. So now carefully see where we started our derivation. So 1 plus 2k times theta is what we borrowed earlier. Ket h is okay, uniform superposition of all the 8 values. That will be illustrated by this expression, root a by n ket a plus root b by n ket b, because it is a uniform superposition. When we take the probability for ket a, it should be a by n. For ket b, it should be to collapse to ket b, it is b by n. So that will be possible only when we take root of a by n ket a plus root b by n ket b. Followed. This is and that is where we started, and in the polar coordinates ket h is equal to this one, and we related this with this, and for small theta is equal to sin theta, and this is what we got. After k rotations, x becomes this one. Theta is replaced by 1 plus 2k times theta. And since our objective is to measure probability of measuring ket A is equal to 1, so okay, that is possible only when this is equated to 1. So that is how we equated sine square of 1 plus 2k times theta to 1. And then this is all a simple derivation. And eventually we arrived at k is equal to pi by 4 times root n. Okay. Now, okay, once one of the three things over, now let us see the some circuit corresponding to Grover's algorithm, then followed by a mathematical illustration. See, all of you know, every algorithm in quantum computing is nothing but a quantum circuit. Okay, we term it as algorithm. So, quantum circuit, there is one important block called oracle, where okay, the core crux of the entire logic is built there, and here this oracle knows the answer. Okay, and we are trying to retrieve the answer which is available with the oracle at the output qubits. So that is the philosophy of any quantum algorithm. It is, you see, it is a simple, we are going to use UF of X in our derivation such that it is defined like this. When X is equal to, when X is a bit pattern, all zeros, when all zeros as input, what, okay, that will remain X, cat X. If one of the bits in the bit pattern is at least one is non-zero, okay, then it is a flipped version of catex. See, or suppose there are 0, 0, 0 to 1, 1, 1. There are totally 8 combinations, 8 permutations. Out of 8 permutations, only one is having this pattern, zeros pattern, all zeros. Remaining seven are having okay, at least okay, at least one is non-zero. So that's why this oracle is defined such that when the bit pattern passes through this U, it will return these two outputs, cat x or minus cat x, depending on the input, whether x is equal to all zeros or not. Okay, this particular oracle is used in the Grover's algorithm. It is out of all oracles, it's a very simple oracle. I repeat again, okay, U of X, this oracle is defined such that when all bits are zeros, then it is cat X. If any other case, it is minus cat X. Okay. Now let us move on to the next slide. So this is where we see the circuit, oracle circuit. For the simplicity sake, we have taken a 2-bit pattern because it will be easy to illustrate. So 2-bit pattern means 0, 0, 0, 1, 1, 0, 1, 1. And only one value is 1, remaining all three are zeros. Okay, so what our algorithm should return? Our algorithm should return the location of this 1, that is 2. Okay, 1, 0 means 2. Followed. See, let us see how it actually performs the job. First, let us see circuit. So there, it is a circuit. All of you know, every circuit will have some specified number of qubits. This is a circuit with how many qubits, you know, how many bits are there here? 2 bits are there. So 2 bits are there means 4 combinations are possible. So 2 bits means 2 qubits here. Here 2 qubits, and this is one additional qubit. So if it is in general, if it is n-bit pattern, okay, we will have n plus 1 qubits. Okay, first n qubits pattern is fed here, 1 qubit is fed here. So if there are n bits, we will have as many as 2 to the power of n binary strings. Are you following? More specifically, if n is equal to 10, okay, it is a list of 1024 elements. So for searching 1024 element problem, we require 10-bit quantum computer, 10-bit plus 1 bit, 11-bit quantum computer. So practically, even if you take 1 billion, 1 trillion, it is all manageable number of bits. Okay, it is even okay. 1,000 means 10, 1 million means 20, 1 billion means 30, 1 trillion means 40. So if it is if it is 40 qubit machine, 1 trillion. Okay, if there are if there is a list of 1 trillion, carefully listen, that searching can be done in a finite amount of time by using a quantum machine, quantum computer of 40 qubits, 40 plus 1, 41 qubits. So that is the power of quantum computer. Let us come back to the problem. Let two bits be given as okay 0 1. Okay, it's a 2-bit pattern, returns either 0 or 1. So this function resembles this table. Find x such that f of x is equal to 1. Here what is n? N is equal to 4, list of 4 elements. And what is a? A is equal to how many target bits are there? Only one is there, that is this. So a is equal to 1. Okay. So then you see, substitute n is equal to 4, a is equal to 1 in the number of rotations required to solve the problem. So substitute here n by 4 by 1. So eventually what I am going to get is 1.071, floor value is 1. That means in one iteration starting from this end to this end, I am going to get the required solution. So like that, okay, if n is equal to say whatever number and you fix a is equal to 1, we will get the number of iterations required to solve the problem. Okay. So just this is the circuit. You see here, let us have a brief introduction about the circuit. It is Hadamard gates, two Hadamard gates. All of you know, Hadamard gate applied on cat 0 gives us 1 by root 2 of cat 0 plus cat 1. So it is concatenation of two Hadamard gates. So 1 by root 2 times cat 0 plus cat 1 into 1 by root 2 times cat 0 plus cat 1. That is how it is elaborated. So you will get a sequence of 4 numbers 0 0 0 1 1 0 1 1. So out of them, 0 0 alone will be unchanged. The sign of 0 0 alone is unchanged. Remaining 3 are changed because I have already briefed about the oracle. So if only when all zeros are there, that will unchanged. But in all other cases, its sign will be changed, flipped. Okay. So once it is done, again we are applying Hadamard gate. Okay, again we are applying U0 and then same oracle, and then again we are applying Hadamard gate. Are you following? So this is the pattern which need to be repeated, this pattern. Now we will see the mathematical solution. Carefully listen. With this, we will understand the circuit thoroughly, how the circuit is designed. Now we see, say there are some conventions. Okay, what is 5 1 5 1? See, this is very important again. See, while analyzing a quantum circuit, we do stage-wise computations. Ket psi 1 is stage 1. Ket psi 2 is stage 2. Psi 3 is stage 3. Psi 4 is cat psi 4 stays 4, cat psi 5 stays 5, cat psi 6 stays 6. I hope you understood. These are the stages, cat psi 1 like that. Okay, now we see cat psi 1. What is cat psi 1? There are two qubits initialized to 0 and 1. So, see here. Here 2 bits 0, 0, here 1. So, that is the essence of cat psi 1. Now, when it comes to cat psi 2, it is a little bit elaborate. How you see here, uh, uh, as I mentioned, it is a multiplication of two Hadamard gates, like 1 by root 2 times cat 0 plus cat 1, and again 1 by root 2 times cat 0 plus cat 1. So 1 by root 2 and 1 by root 2 is equal to 1 by root 4. So 0, 0, 0, 1, 1, 0, 1, 1. So this is how cat psi 2 appears. First part of cat psi 2 appears. Okay, it's not, it is concatenated with what is this? Minus, cat minus. Why cat minus? All of you see here, when Hadamard gate is applied on cat 1, the resultant is cat minus. When Hadamard gate is applied on cat 0, resultant is cat plus. So since we applied cat 1 on Hadamard gate, it is minus. So we got concatenated, we concatenate this with minus here. Now you see this convention is very, very important. People confuse here. Now we see here it is a bit pattern. 0, 0, 0, 1, 1, 0, 1, 1 is a bit pattern. But see, since it is a 2 qubit, it is manageable. If there are 10 qubits, that bit pattern will be very lengthy, and the Hadamard gate applied when it is again a very compounding impact will be there. So what we do, we convert this bit pattern into decimal pattern, decimal numbers. 0, 0, 0, 1, 0, 1 becomes 1, 1, 0 becomes 2, 1, 1 becomes 3. So this decimal number is actually not a decimal number. It is an equivalent of a binary number. Okay. So this notation is very popular because it will make the entire algebraic expression very compact. So this is how this value, this expression is converted to this brief form, where x is equal to 3 means cat 3. Cat 3 actually mean cat 1, 1. Is it clear?
Yes, sir.
Okay. Now we see, all of you carefully see now. Now we are passing through third stage. Third stage. What is the third stage? Cat psi 3. You see here. This is the third stage, cat psi 3. Now carefully see. Oracle, I told you, Oracle knows. It is like, okay, it's like some game. Okay, I remember something, and you will be trying to pose questions, and eventually you get what is there in my mind. No, that is similar kind of game. You see here, Oracle knows where is the answer. Where is the answer? It is at this location. Are you following? So Oracle knows, but we do not know. See this. So that's why minus 1 to the power of f of x. See, what is f of x? 0, 0. Here it is 1, and here it is 0. So phi 3 is doing, cat psi 3 is doing one very trivial operation, but very important operation, where okay, see here, when this is the elaborated form, where actually our answer is there here minus okay, third location. So f of x is equal to, see carefully, f of x is equal to 0. When f of x is equal to 0, minus 1 to the power of 0 is equal to 1. So the input and output will remain same. When f of x is equal to 1, minus 1 to the power of 1 is equal to minus 1. So for this, the third bit sign changes. Third bit sign changes. You see here, that is what happened. Here, cat psi 2 is this one, ket psi 2, but when it comes to ket psi 3, third bit sign change it to minus. Followed. Third bit sign changes to minus. Are you following? Remember, you will get a doubt. Okay, when it is solved, okay, we can get it from here itself. There is a need for going till the end and carrying out multiple iterations. Remember, you cannot get, okay, you can get the outputs only at this stage. Okay, this is all internal. We cannot, decode. See, Oracle knows, but remember that retrieval of known things to the Oracle is the job of quantum computing. Remember. Remember, you see, when we are inventing something, that is not actually invention, it's a kind of discovery. It is there, okay. If something is not there in your brain, it will never come, okay. If something, okay, coming out means you have given a conducive environment to come out. So that is how we should understand. Okay, so here ket psi 3 is equal to this one. So Oracle knows where that answer. So that sign is changed to minus, and this is eventually we got. Ultimately, that ket of minus is there, which is simply appended. And now you see. Now we need to apply Hadamard gate. This Hadamard gate. Okay, it is a concatenation of two Hadamard gates. All of you carefully listen. It's a concatenation of two Hadamard gates. So now what is happening? All of you carefully see. 1 by 2. Okay, H Hadamard gate applied on 0 0. Okay, 0 0 1. See, here it is 0 0. It is 0 1. 2 means 1 0. 3 means 1 1. I hope you followed. Now, just for understanding sake, I am again decoding into a binary string from decimal string. 0 means 0 0. 1 means 0 1. 2 means 1 0. 3 means 1 1. Now we see Hadamard gate applied on ket 0 0 is 1 by root 2 times ket 0 plus ket 1 into 1 by root 2 times ket 0 plus ket 1. Are you following? And 1 by root 2 into 1 by root 2 is equal to 1 by 2. Ket 0, ket 0, ket 0, 0, ket 0, 1, ket 1, 0, ket 1, 1. So this is a simple algebraic kind of expansion. I hope you understood. So now this whole expansion is for only this term, first term. Now there is a second term, there is a third term, there is a fourth term. So there is a compact way of representation. So I'm using this table. So carefully listen. 0 0 means a Hadamard gate 0 0 is this. These are the coefficients of ket 0 0, ket 0 1, ket 1 0, ket 1 1. So what is the coefficient of ket 0 0 plus 1? Ket 0 1 plus 1, ket 1 0 plus 1, ket 1 1 plus 1. I hope you understood. Similarly, so this first row indicates expansion of Hadamard gate applied on 0 0. Now let us see Hadamard gate applied on 0 1. 0 1 means the expansion is this. Okay, when it is expanded further like an algebraic expression, it will be like this. 0 0 plus and then 0 minus 0 1 minus 1 0 k plus and then 1 1 minus. Now we see this is second row in the table. Plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. And similar fashion we need to do for ket 1 0. Whatever value we get to apply minus, so minus ket 1 0. This is the resultant. Finally, H11, okay, plus, minus, minus, plus. So now altogether we are having as many as 16 expression, 16 terms in the expression. So now what is the coefficient of 0 0 is 3 plus and 1 minus, so plus 2. and the coefficient of 0, 1 is minus, okay, plus 1, minus 1, minus 1, minus 1. Are you following? So it is minus 2. And it is again plus 2, again it is plus 2, because pluses are 3, minus is 1. So ultimately what I am getting, what I am getting at this level, psi 4, carefully see, psi 4, what I am getting is 1 by 2 times, okay, ket 0 minus ket 1 plus ket 2 plus ket 3. So this is the end result after stage 4. Is it clear? This this table form is clear to everybody. It is only table form to put the things in a compact form. Okay, because it's a 2-bit string. Okay, you can even expand it. But if it is a 3-bit, 4-bit, it will be very difficult. We will get confusion unless we put a table form like this. So is it clear?
Sir, can you please explain how did you write psi 4?
Psi 4. You see here, all of you see carefully. Here, this is psi 3. I hope you understood psi 3. Ket psi 3 is
Yes, sir.
okay?
Yes, sir.
Ket psi 3, how did we get minus here? Only one bit
Because
got, because Oracle knows that third bit is the target. So f of x is equal to 1 there. When f of x is equal to 1, minus 1 to the power of 1 is equal to minus 1. That's why we changed the sign of third bit. Okay. So this is the output of at stage 3. Now we see, now this is actually, I told you, it is a replication. 0 means 0, 0. 1 means 0, 1. 2 means 1, 0. 3 means 1, 1. Is it clear?
yes, sir.
Now we are moving to the stage 4. What is there in stage 4? In stage 4, there is a Hadamard gates. There are 2 bits applied. So the Hadamard gate is invoked 2 times. One for first bit, one for second bit. So see here, first this 0, 0 means 0, 0. I applied Hadamard gate. 1 means 0, 1. I applied Hadamard gate. 2 means 1, 0. I applied Hadamard gate. 3 means 1, 1. I applied Hadamard gate. This is clear?
Yes, sir.
Now we see, I am carefully elaborating one term at a time. So this whole expansion is okay corresponding to h of ket 0, 0.
Yes, sir.
Okay, so only one term I expanded. How I got Hadamard gate applied on ket 0, 0. Hadamard gate applied on ket 0 is equal to 1 by root 2 times ket
1 by
0 plus
root
ket
2,
1.
ket 0 plus ket 1.
And the second second bit is also 0. So again 1 by root 2 times ket 0 plus ket 1.
Yes, sir.
So 1 by root 2, 1 by root 2 is equal to 2. So
1
like in
by 2.
algebra variable 0 into 0, 0 ket 0, 0, ket 0, 1, ket 1, 0, ket
Ket
1,
1,
1.
1.
So I got an expansion. This expansion is for only first Hadamard gate.
Yes, sir.
Followed. Now, what I am doing, I am putting this expansion as one row in the table. One row in the table. This row correspond to ket 0, 0. So I put and at the left hand side, I put 0, 0. And you see, every column is given a description. What is the description? Okay, this one 0, 0, 0, 1, 1, 0, 1, 1. I am moving my cursor. Is it visible to you?
Yes, sir. Yes, sir.
Very good. So 0, 0, 0, 1, 1, 0, 1, 1. Now,
Yes,
what
sir.
is the coefficient of ket 0, 0, 1 plus 1?
Hmm.
Coefficient of 0, 1 plus 1. Coefficient of 1, 0 plus 1. Coefficient of 1, 1 plus 1. So this first row in the table is contributed by cat H00, H of cat 00. Are you following? Now let us move on to the second Hadamard gate. H of cat 01. H of cat 01. So you see here 01. Are you following? So when it is expanded, I got this. So in the now I'm adding it as a second row in the table. So this is corresponding to 01. So it is 01 here. And you see the coefficients. It is +1, -1,
Minus one,
+1,
plus
-1.
one, minus one.
So +1, -1, +1, -1.
Yes, sir.
In the similar manner, I haven't done the third part and fourth part. We can do similar expansion. Here, the first term will be 1 by root 2 times cat 0 minus cat 1. Second term will be cat 0 plus cat 1.
Yes, sir.
And then whatever value you get, apply minus sign because it is there.
Minus on to that.
So, coefficients part alone you take and then you put it in the third row. And corresponding to the last term, that will be contributing fourth row.
Yes, sir.
So now these are all coefficients of cat 00. So all the coefficients of cat 00 can be summed up. So +1, +1, -1, +1. So +2. Similarly, all the coefficients of cat 01 -2. All the coefficients of cat 10 +2. All the coefficients of +1 cat 11 +2. Are you following? So now what I am actually doing? I am doing. Now we see carefully. All of you carefully see what it is actually giving us. Giving us two times of uh, two times of cat 00 minus 2 times of cat 01, okay, plus 2 times of cat 10 plus 2 times of cat 11.
Yes, sir.
Okay, so now 1 by root 2, 1 by root 2 is this is 1 by 2. So it has contributed to take 2 out common term. So what will be left inside? Cat 0 0 0 minus cat 1 0 1 plus cat 1 1, sorry,
Cat 2, cat
0
3.
plus cat 1 1. Followed?
Yes, sir. Yes, sir.
Now we see now we carefully see here 1 by 2 is there at the outermost thing. Each Hadamard gate is contributing 1 by 2. So 1 by 2 into 1 by 2 is equal to 1 by 4. Numerator, there is a term 2 common. So 2 by 4 becomes 1 by 2. I repeat carefully.
Yes, sir.
See, cat psi 4 is 1 by 2 times this. Okay.
Yes, sir. Yes, sir.
Each Hadamard gate term contributes 1 by 2.
Yes, sir.
So if you bring this 1 by 2 out, it will be 1 by 4. 1 by 2 into 1 by 2.
Yes, sir. Understood.
So, but here, when we are summing up all these terms, so it is contributing two is a common term here. 2, okay, here everywhere it's a factor of 2. So I take out 2. So 2 by 4 times, okay, this is cat 0 minus cat 1 minus plus cat 2 plus cat 3. Clear?
Yes, sir.
Yeah, see, it is very it's a simple algebra term, and there is nothing great in it. This is 1 by 2 and every term inside the parenthesis contribute to 1 by 2. So this 1 by 2 can also be taken out, so it becomes 1 by 4 outside. So inside there are how many terms? 16 terms are there. When I add up all these 16 terms, 2 times of cat 0, 0, 2 times minus 2 times of cat 0, 1, like that. Another 2, okay, is emerging. I take out the 2, so it becomes 2 by 4 of cat 0, 0, cat 0, 1, cat 1, 0, cat 1, 1.
Yes, sir.
Okay.
Understood.
So this is the output at stage 4. Stage 4. This is. Are you following? Now I am applying U0. What is U0? U0 is 1, 1, where it retains the first, when see, I have given the oracle definition here, two oracles definitions. If you observe here, you see, U0 is defined this way. UF is defined, okay, this is what we have seen earlier. Okay, this is UF. See, I defined two oracles. One is UF and second one is U0. U0 is, how is it defined? When all bits are zeros, then no change. For all other cases, there is a change of sign. So I apply that. That is your cat. This is cat psi 4. Okay, already there in the previous slide. I just wrote again. Okay, cat psi 4 is equal to 1 by 2 times cat 0 minus cat 1 plus cat 2 plus cat 3. That is the output available here. Cat of psi 4. I wrote it once again. Now U0. Next gate is U0 gate. What is U0 gate? It flips everything, every state except to 0 state. So then this is 0 state. This is unchanged. This minus becomes plus, plus becomes minus, plus
Minus.
becomes
3
minus,
also becomes minus.
and this will remain cat of minus sign. Okay. Now we see. Lastly, what we are doing, we are applying once again Hadamard gate. We are applying once again Hadamard gate. So when Hadamard gate is applied on this, okay, okay, this is 0, 0, 0, 1, 1, 0, 1, 1. All of you know, okay, how to perform these computations. We know how to perform this computation. Same procedure what I followed earlier is repeated here. Are you following? By doing so, what I am getting, see, very surprising thing. Okay, when see, there are two minus, so correspondingly two minus. So then the contributions, individual type contributions are placed. So this is the coefficient of cat 0, 0. This is the coefficient of cat 0, 1. This is the coefficient of cat 1, 0. And this is the coefficient of cat 0, cat 1, 1. Are you following? Now we see. So when it is brought to this, what I am going to get, cat of psi 6 is equal to 1 by 2 times into 4 times of cat 1, 0. Are you following? 4 times of cat 1, 0. And remember, so 2 cancels, so 2 times cat 0. Sorry, 2 times cat 1, 0. So see, final expression, what is this actually? This is x. So the conclusion is the element is found at location cat 10. Cat 10 means convert into the binary decimal equivalent, that is equal to 2. Okay, you see here where actually this is there. It is in the second location 2. Are you following? So the element is found at location 2. That's all. Okay, because it took only one iteration. Okay, it is stopped here. Had it been repeated for one more iteration, what we do, we carry out all these computations from here to here. Again, we will carry out all these computations. Sorry. Okay, so it is, see, one important thing here is, carefully listen. One traversal from left hand side to the right hand side is considered as one iteration or one time instance. Okay, it's not like if there are 6 stages, 6 into n, no. Okay, this is how the time complexity is measured in the quantum circuits, quantum algorithms. Even if it is a concatenation of several gates having 10 stages, okay, up to psi 10, there are there. Everything is considered as one cycle. One cycle means one clock, okay, clock pulse. Are you following? So this that means you take this case. There are it's a list of 4 elements. So we identified the right location with the order of one. Order of one. So that is the power of quantum computing. So it's a beautiful illustration. I remember it is you need to practice it more, okay? Because as I mentioned, Grover's algorithm is having its own significance now in the machine learning. People are using the variant of Grover's algorithm in the machine learning for the searching space. Okay, now that is one of the very key research areas. Okay, remember in this entire explanation, we seamlessly integrated algebraic simplifications as well as quantum identities and quantum rules. So you must be able to understand which part is of quantum stuff and which is algebraic stuff. Okay, so this is very important. So particularly you take this one. This is whole thing is algebraic. No actually anything for quantum stuff here, except concatenation of two Hadamard gates. So everything is simply algebraic expansions. Yeah. So this is all about Grover's algorithm. So I invite questions.
Sir, what advantages does it carry over classical hashing? Because hashing also, we generally say it completes in order of 1 unit of time.
Hashing order of one only in ideal case, only best case.
Hmm.
Okay.
When there are no collisions.
See, hashing is not considered as the most optimal solution.
Hmm.
Hashing is having its own challenges.
When we have collisions, definitely,
Yes. Yeah, the searches will increase. Okay.
yes, sir.
And remember, hashing is memory intensive. Okay.
Hmm.
Uh, yeah, it is having its own limitations. Okay. Practically for larger numbers, larger list. Okay.
Hmm.
You may have to go for multiple iterations.
Or maybe we might go for double hashing also, depending on number of
Yeah.
keys or number of collisions. We might need to go for double hashing.
Double hashing, open hashing, all these things are okay. Okay, but see, they are all considered as okay, not as see when we are trying to get an advantage. Okay, with a cost. Okay, with a if you closely observe, just like for example, you see sorting techniques. Heap sort is the most preferred sorting among all the classical sorting techniques because it's of okay, even worst case also order of n log n complexity like that.
Yes, sir.
Okay, for every algorithm, searching algorithm, we see there is a best case, average case, and then worst case. Okay, so we need to consider the worst case scenario. So here,
Okay.
in the worst case scenario, also it is okay, a stable solution.
Okay. Okay.
Yeah.
Maybe based on that, we can conclude this gives a better performance compared to classical hashing and heap sort.
Certainly, certainly. See, remember root n of okay. It is amazing. It is one of the most okay. In fact, as on date, in any domain, whether it is computing or classical digital domain, okay, this algorithm is considered to be the best algorithm, Grover's algorithm for searching.
Okay.
Yeah.
Mhm. And what would be the advantage of repeating the number of qubits, sir? In order to represent a single zero, we are repeating it as 00, 2 qubits. So what
Uh,
would be the advantage of that?
The advantage means it's a compact. For example, you see x is equal to 0 to 16. Okay. Or x is equal to 0 to 32. Assume 32 or even 32. That means it's a bit pattern of 5 bits. Are you following? So it will be. It is not. They see when we are when we are writing something on the paper. Okay, the simplification will be very boring. Like it will be very cumbersome. It will be not so pleasing. So that's why we are converting. It's only a convention. Okay, if you are happy with the bit pattern, you go with the bit pattern. It's you don't have to convert into decimal pattern, decimal equivalent.
Yes,
Remember,
sir.
at every critical time, I am converting back into equivalent bit pattern. 3 is converted into 1 1, 2 converted into
Yes,
1
sir.
0, like that. Okay, it
Hmm.
is just okay a convention for particularly we require it for Fourier transforms, quantum Fourier transforms, and all. They are okay a little bit lengthy expansions. So this decimal conversions will help us.
And how do we know how many number of I mean, how many number of stages should be there in a cycle?
That's what. Okay, now okay, I'm coming back. Now you see how many stages are there. You see here, what is known to us. What is known to us? How many numbers are there in this is known to us. Okay, here it is 8. How many numbers are there in the
Yes.
list is known to us. Are you following?
Huh. Yes,
And
sir.
and assume there is only one target. So small a is known to us. If
Okay.
small a is known, uppercase, okay, if small a is known to us, okay, then carefully see here. Uh, uh, this number of iterations expression involves only two things. One is how many elements are in the list. See, it's very simple. How many elements are in the list? How many target elements are there in the list? Suppose there is only one target element which we are searching in the list, and okay, that then a is equal to 1. If the list is having n is equal to say 1000, so n is equal to 1000. So for arriving at number of iterations, okay, we don't have to do complex expressions or any big terms. Only all that you need is list size. How many elements are there in which you want to search for an item? If the item to be searched is only one, then a is equal to 1. Then it is simply pi by 4 root n minus half. That many iterations. It is, remember, that many iterations are sufficient. That is bound to happen. That is bound to happen. You see here. See, probability for measuring cat A equal to 1. So this H. So this is X. Okay, X aligned with cat A. Are you following? So, in the geometrical sense, it is aligning with cat A, but in the collapsing sense, it is probability is equal to 1. So probability 1, so when we are equating to 1, when we are equating it to 1, it is bound to, okay, remaining the expression is simple mathematical expression. So here in this whole derivation, I haven't used any quantum knowledge. Where I used quantum knowledge, I used quantum knowledge in this, our aim. Probability of measuring cat A is equal to 1. This, for you to convince, you should understand quantum computations. It is like collapsing a quantum qubit, collapsing a qubit to a state. Which state? Cat A. So I'm putting it in other way. So aligning with cat A. Okay. So this particular derivation is the contribution of quantum computing here. And of course, this part is also quantum computing. Cat H is equal to root A by n cat A plus root B by n cat B. Because it is a simple superposition wherein we are giving all elements equal probability. All elements equal probability. So probability for a successful search is equal to A by n. Probability for unsuccessful, okay, this one is B by n. Okay, initially. Are you following?
Yes, sir.
See,
Yes, sir.
initially assume there are 1000 elements. Only one is A. Only one is the required element. So probability for successful is 1 by 1000. Probability for unsuccess is 999 by 1000.
1000.
Ah,
Yes, sir.
so initial hypothesis is built from the quantum theory. And remember, if you are familiar with Hadamard gate, okay, no complexity involved anywhere in this whole algorithm. Only thing you require is
Yes, sir.
Hadamard gate functioning. Okay,
Yes, sir.
and these are all reflections. First reflection about x-axis, second reflection about cat h. Okay,
Mm.
yeah. So
Sir,
I will do a little modification to the slides, and I will give the slides to the coordinator. Please
yes, sir.
use these slides. Okay, try to practice the algorithm more number.
Sure, sir. Thank you, sir.
Thank you, thank you.
Respected Professor Kamakshi Prasad sir, on behalf of the Department of CSC, A&ML, KMIT, and all participants, I sincerely thank you for delivering such an enlightening session today. The talk this evening has given us valuable insights and broadened our understanding of Grover's algorithm. The clarity of your explanations and the examples you shared have truly added great value to our FDP. I am confident that the participants have gained knowledge that will greatly benefit their academic and research pursuits. We are deeply grateful for your time, effort, and commitment in sharing your expertise with us in spite of your busy schedule. We look forward to more opportunities for learning and collaboration in the future. Thank you once again, sir. Thank you.
Thank you. Thank you.